For half a century, the moon remained a destination for visitors, short stays, flags, and footprints. But as we pivot toward the Artemis era and the International Lunar Research Station, the goal has shifted. If humans are to remain, the base itself must function as a complete life support and protection system. This is the story of how we build a home where none was intended to exist. The moon is perhaps the most hostile environment ever considered for long-term human habitation. Without an atmosphere or a magnetic field, the surface is bombarded by solar and galactic cosmic radiation. Temperatures swing wildly from 127 degrees Celsius in the sun to minus 173 degrees in the shade. Then there is the dust, lunar regolith, razor-sharp, electrostatically charged, and pervasive. Unlike Earth, the moon lacks a global magnetosphere. Galactic cosmic rays and solar particle events strike the surface with high energy, capable of damaging both human DNA and sensitive electronics. Shielding isn't just a comfort, it is a fundamental survival requirement. We must design for a 10-year mission horizon, accounting for the 11-year solar cycle and the unpredictable intensity of solar flares. Habitats require absolute pressure integrity. Most current architectures utilize a dual-layer approach, an inner inflatable or rigid module to hold the atmosphere and an outer shield to handle the environmental load. A single micrometeorite traveling at several kilometers per second can breach a standard hull. Protection requires mass, and mass is expensive to launch. Radiation shielding is the primary driver of lunar architecture. To reduce exposure to Earth-like levels, a regolith layer of 2.5 to 3.5 meters is required. This mass also serves as thermal ballast, stabilizing the habitat's internal temperature against the external extremes. By burying our homes, we leverage the moon's own geological history for protection. One alternative to surface shielding is the utilization of lunar lava tubes. These natural subterranean caverns, formed by ancient volcanic activity, offer immediate protection from radiation, micrometeorites, and extreme temperatures. Mapping sites like the Marius Hills Hole suggests caverns large enough to house entire cities, sheltered by hundreds of meters of solid basalt, a ready-made lunar fortress. The future of lunar construction lies in additive manufacturing. We are moving beyond simple digging to sophisticated 3D printing using the soil beneath our feet. Sintering, melting, and geopolymer processes are all being refined in labs around the world to turn loose dust into solid structural rock, allowing us to build landing pads, roads, and habitats autonomously. Solar sintering is one of the most promising techniques. By concentrating sunlight through Fresnel lenses or using high-powered lasers, we can fuse regolith particles without any chemical binders. Projects like Regolite have demonstrated that we can print structural shells layer by layer, essentially baking the base into existence using the moon's own energy source. The distinction between sintering and melting is critical. Sintering fuses particles at around 1100 degrees Celsius, preserving some porosity. Full melting, occurring at 1600 degrees, creates a dense basalt-like glass. Each has its role: sintering for walls and roads, melting for high-pressure seals and structural beams where maximum density and strength are paramount. Strength is the key metric. On Earth, high-performance concrete reaches 35 megapascals. On the Moon, the lower gravity reduces our structural requirements to roughly 6 megapascals. While early solar-sintered samples achieved only 2.5 megapascals, new geopolymer mixes and optimized melting cycles are closing the gap, aiming for space-grade durability. To build with regolith, we must understand its chemistry. It is primarily composed of silicate and oxide minerals like plagioclase, pyroxene, and olivine. The lack of water and wind means these grains are not rounded like earth sand. They are jagged, glass-heavy, and chemically reactive, making them both a hazard and a resource that we are only beginning to master. Construction is only half the battle. To stay, we need oxygen, water, and fuel. This is the realm of in situ resource utilization, or ISRU. The lunar soil is a chemical treasure chest. Approximately 40 to 45% of regolith by mass is oxygen, trapped within silicate and oxide minerals, enough to sustain a global civilization for millions of years. Molten regolith electrolysis, or MRE, is a primary extraction method. By heating the soil to over 1600 degrees Celsius and passing an electric current through the melt, we can release pure gaseous oxygen at the anode. The byproduct? Molten metal alloys, including iron and aluminum, that can be cast into structural components on site. Blue Origin's Blue Alchemist program has revolutionized this field. They've demonstrated the ability to produce silicon with 99.999% purity directly from simulated regolith. This isn't just for breathing, it's for building high-efficiency solar cells to power the base itself, creating a self-sustaining cycle of energy and material production. Another pathway is carbothermal reduction. By reacting regolith with methane at high temperatures, we can extract oxygen with high efficiency. Systems like the Air Pioneer reactor are designed to be compact and modular, providing a reliable oxygen supply for a growing crew without the extreme power needs of full electrolysis, making them ideal for early-stage habitats. The economics of ISRU are based on energy yield. Current studies show we can extract roughly 31 milligrams of oxygen per kilowatt hour. While efficiency is currently around 2.5%, the scale of the lunar resource means even low-efficiency systems can provide massive quantities of life-sustaining gas, provided we have the power to drive them. The most difficult power challenge is the lunar night, 14 Earth days of absolute darkness. Solar power alone is insufficient. We must rely on massive energy storage, such as hydrogen fuel cells using ISRU water, or fission surface power units, compact nuclear reactors capable of providing steady, reliable electricity for decades, even in the coldest lunar shadow. Beyond oxygen lies the Moon's most precious liquid, water. In the permanently shadowed regions of the lunar poles, places like Shackleton Crater, temperatures never rise above -233 degrees Celsius. These are cold traps, where water ice has accumulated over billions of years, protected from the sun's reach by the crater's high walls. Water is the ultimate propellant and life support resource, but extracting it is a monumental challenge. The ice is mixed with regolith in a concrete-like matrix. Mining it requires massive energy for excavation and heating, all while operating in the extreme cold and absolute darkness of the lunar South Pole, where equipment can fail in minutes without constant heating. Missions like China's Chang'e 7 are leading the hunt. Equipped with a mini-hopping probe, this mission will venture directly into the darkness of the craters to conduct in-situ analysis. We need to know the purity of the ice, currently estimated at 75 to 85%, and its depth before we can scale up industrial mining operations. Accuracy is everything. Inside the base, every drop counts. The Environmental Control and Life Support System, or ECLSS, must achieve near total closure. On the International Space Station, we recycle 93% of the water. For a lunar base, we aim for 98% or higher to minimize the cost of resupply from Earth, which can reach tens of thousands of dollars per liter. Oxygen recovery is driven by the Sabatier reaction. By reacting waste carbon dioxide from the crew with hydrogen, we produce water and methane. The water is then electrolyzed to recover oxygen, while the methane can be utilized as a rocket propellant. It is a closed loop that mirrors the biogeochemical cycles of Earth, essential for long-term survival. Lunar dust is the silent enemy of life support. It is highly abrasive and electrostatically charged, threatening to clog filters and degrade mechanical seals. A lunar ECLSS must incorporate advanced electrostatic and mechanical filtration to keep the internal air pristine for months on end, protecting both the hardware and the delicate lungs of the crew. Safety begins with filtration. Bioregenerative systems are the ultimate goal. By integrating plants into the life support loop, we can produce food and additional oxygen while naturally scrubbing CO2. These greenhouses are complex and power-hungry, but they provide a critical psychological link to Earth for long-duration crews. Green space is not just for air, it is survival space for the spirit. Maintaining a permanent base requires a robust communication grid. With the Moon's rotation, direct line of sight to Earth is not always possible. Relay satellites like Kuichao-2 and the Orbital Lunar Gateway ensure high-bandwidth, near-continuous data and video streams. These links are the lifeblood of mission control and the emotional tether for the crew living 384,000 kilometers away. But engineering the habitat is only one part of the equation. We must also engineer for the human mind. The Moon is a place of profound isolation, further from home than any human has ever lived. The psychological toll of living in a confined, high-danger space for months on end is real and measurable, affecting everything from sleep to decision-making. Our best laboratory for lunar psychology is Antarctica's Concordia Station. During the 9-month winter over, crews are completely isolated in a dark, extreme environment. Data from these missions shows a phenomenon called psychological hibernation, a decline in coping mechanisms and positive emotions as the dark winter progresses, mirroring the conditions we expect on the Moon. Isolation literally changes the brain. MRI scans of Antarctic crews have shown a transient decline in gray matter volume, particularly in the hippocampus, which is linked to memory and spatial navigation. This decline is strongly correlated with poor sleep quality and the disruption of circadian rhythms caused by the lack of natural day-night cues, a critical design challenge for lunar architects. Medical capability must be largely autonomous. Evacuation to Earth requires days even under ideal conditions. A lunar base must be equipped with surgical, diagnostic, and pharmaceutical resources capable of handling emergencies without immediate Earth intervention. The crew are their own first responders, doctors, and pharmacists. We fight back with design and discipline. Regular exercise has been shown to mitigate brain volume loss, while private spaces and reliable high-bandwidth communication with Earth are non-negotiable requirements for mental health. Habitat design must prioritize visual variety, meaningful work, and immersive leisure to keep the crew resilient and ready for the next mission. We are at the threshold of becoming a multiplanetary species. The technical challenges of the Moon are immense, but they are the necessary proving ground for the leap to Mars. From the first robotic surveyor to the first permanent resident, the Moon represents the final step before we venture truly deep into the solar system. We are learning how to live among the stars. Building a place to live on the Moon is not a single engineering problem. It is a simultaneous solution of structural, chemical, and biological challenges. It is the greatest construction project in human history, a bridge to the stars, built one layer of regolith at a time. The Moon is no longer just a destination. It is the starting point for our future as a spacefaring species. The lunar South Pole is a landscape of extremes, of perpetual shadow and peaks of eternal light. It is the most valuable real estate in the solar system. We are no longer looking for a place to leave footprints. We are looking for a place to build a home. But between us and that reality stand walls that engineering alone cannot climb. This is an analysis of the invisible walls, the legal, economic, and technical barriers that define our second attempt at the Moon. The first wall is legal and geopolitical. In 1967, the Outer Space Treaty established that no nation can claim sovereignty over the Moon. It was a document designed for a Cold War, not a lunar economy. The treaty is silent on resources. Can you own what you extract? The Artemis Accords, now signed by over 40 nations, argue yes, that extraction is not appropriation, but not everyone agrees. The Accords introduce safety zones to prevent harmful interference. To some, these are essential for operations. To others, they look like the first step toward territorial claims. China and the Russian Federation are developing the International Lunar Research Station. We are witnessing the emergence of two parallel legal and operational regimes in the same polar region. Beyond the law lies the physical wall of the lunar night. 350 hours of darkness, temperatures that can fracture steel. Survival here is a question of energy density. Solar power alone is insufficient for a permanent base. To bridge the night with batteries would require a mass penalty that no current rocket can afford. We need a power source that doesn't quit. The solution is fission surface power. NASA and the Department of Energy are targeting a 2030 deployment of a 40 kilowatt class reactor, enough to power a small neighborhood for a decade. Unlike terrestrial plants, these lunar reactors use Stirling or Brayton converters to turn heat into electricity with no moving parts exposed to the dust. It is silent, continuous, and essential. The second wall is economic. Apollo was funded like a war, peaking at 4.5% of the US budget. Artemis is a marathon, running on less than 0.5%. Efficiency is the only way forward. Sustainability means breaking the Earth dependence loop. We cannot afford to ship oxygen and water from Earth indefinitely. We must learn to live off the land. This is ISRU. Oxygen is locked inside the lunar rocks. We have two paths: hydrogen reduction, which is mature but limited, and molten regolith electrolysis, the holy grail of lunar chemistry. MRE doesn't just give us air, it gives us steel and silicon for 3D printing. We aren't just extracting resources, we are mining the foundations of a new civilization. Protection is paramount. To shield against cosmic radiation, we must bury our homes under meters of lunar soil. The moon is not a surface to live on, it is a material to live within. The roadmap is no longer abstract. It is a sequence of robotic precursors, orbital gateways, and surface outposts. The cadence is increasing. The barriers are under active attack. The moon demands everything from us: technical precision, legal clarity, and political will across decades. If we meet those demands, we cross a threshold. We become a species that can live on more than one world. We began with an ambition that was larger than footprints and flags. Not another 3-day visit, but a place where people could live and work for months. A sustained presence on the high ridges of the South Pole, where near constant sunlight and ancient shadowed ice sit only a short distance apart. That ambition has not disappeared. It has only become more complex. Two major international blocs are now racing toward the lunar surface. On one side, the Artemis program, a coalition of over 40 nations led by the United States, focused on commercial exploitation and Mars preparation. On the other, the International Lunar Research Station, led by China and Russia, with partners including Pakistan, Belarus, and Egypt. The environment they face is unrelenting. The moon lacks a global magnetic field, exposing the surface to primary galactic cosmic rays and solar energetic particles. A critical component is the albedo neutron field. When high-energy particles impact the regolith, they trigger spallation reactions that produce secondary neutrons. These neutrons add 15% to the total dose. Paradoxically, thick regolith shielding can increase the flux of secondary neutrons if not managed correctly. Advanced dosimetry, like the fast neutron detector, is now vital. It measures neutrons above 100 mega-electron volts, which penetrate deep into human tissue. Then there is the dust. Lunar regolith is chemically reactive and highly abrasive, the result of billions of years of micrometeorite bombardment. Plume surface interactions are a systemic threat. Engine plumes can loft dust at high velocities, effectively sandblasting any infrastructure in the vicinity. Active mitigation systems like the electrodynamic dust shield use electric fields to remove dust from solar panels and seals, a technology already being flight tested. Survival through the 14-day lunar night requires power sources independent of the sun. The baseline is a 40 kilowatt nuclear fission reactor. For larger bases, 100 kilowatt systems are planned. These will likely use Brayton cycle engines, which offer superior efficiency for high power demands in space. But the most complex variable is the human body. We know much about microgravity, but almost nothing about sustained life in 1/6 gravity. Chronic low gravity leads to myocardial atrophy, a direct weakening of the heart muscle. Red blood cell volume also drops, a condition known as space anemia. Experiments with bioengineered heart tissue on the space station have already shown that low gravity directly impairs the rhythmic beating of cardiac cells. Bone density loss in these environments occurs at a rate 10 times faster than osteoporosis on Earth. Whether 1/6 gravity can halt this remains an open question. To stay, we must use the land itself. Molten regolith electrolysis heats the soil to 1600 degrees Celsius to extract life-sustaining oxygen. In 1/6 gravity, gas bubbles do not detach as easily. Managing this fluid physics is the difference between a functional base and an engineering failure. Water ice in permanently shadowed regions is the ultimate prize. Techniques like the Rodriguez well are being adapted to melt and pump subsurface ice. We are no longer just visiting, we are building the infrastructure of a multiplanetary species. The high ground of the South Pole is the foundation. Crossing this threshold requires every ounce of our technical and political will. The moon is not a destination, it is a beginning,